Um, we can browse some web pages with tools and give a few demos. So this is the homepage of, or this is a page of with tools from my research group where I work. So each box is a link to a demo of one of the tools. So I took a few examples. AGL is an automatic graph layout tool, and it's developed by Leif Nachmansson, who's from Ekaterinenburg. And you, the input to AGL is a description of a graph, and then it automatically draws the graph. Let's see, so here's the bar to see the rest of the graph. And this graph happens to be a dependency graph of the tools that are on the demo page. So it's sort of self-referential. So you'll see the graph layout tool is used in other environments where it's useful to draw graphs. It also ships with the Visual Studio, both 2010 and 2012, the newest one. 2013, I guess it's going to be called. No, it's 2012. Yeah. Where that allows you to draw architecture diagrams of systems and explore their dependencies. But then we also use them in this cottage industry of research tools. And then, of course, another tool that's a part of this graph is one that I work on called Z3. So here, and there's a number of tools that then use Z3. So it's a low-level tool, and then there are higher-level applications built on top of that. So here's another example of a graph. Should be larger. Yeah, so it's so big that it doesn't really show. Let's see. What's the command? Command minus? Forget. Yeah. We'll get it smaller. So it draws a large graph, and so one feature of AGL is that it allows to draw bundle edges, so that you can see. So if you don't bundle the edges, the edges would be everywhere on the map. But here they're nicely bundled like railway tracks, and that gives you a easier way to read what approximately reaches what. So that's a very nice feature of this. So the smarts of the tool is the algorithms for bundling the graphs and drawing the edges nicely. So pics are fun. So if you get immensely bored during the talk, here's a fun site to look at. There should be some, depending on what version of the browser. And I'm not familiar with the Safari browser, so let's see. No, let's drop it. But the point with Pics for Fun here is that this is a test case generation tool, and this example asks whether we can find an array and an input that such that value of the array at this input plus 2077 equals 42. So if you do normal random test case generation, you start random values of this, and you never get to the magical values of V and I that exercises this bug. So it uses Z3 to find a solution that will exercise the bug. So the solution here is on the last line, and it's a singleton array, an array with one element, and the index I is 0, and well, it's subtracted basically 42 subtracted by 2077. There's so depending on which whether your browser allows HTML5, it also acts as a graphical interactive development environment here. We have a much fancier development environment for the Windows Phone, and this allows you to program the phone on the phone. So I can show you to you after the talk on my phone. So there's some nice small scripts you can write, yeah. So that's pretty cool. Then there's a Python interface for Z3, so here's a Python script that calls Z3. So all of this is Python code, and we use overloading of Python to declare variables x and y to be reals, and then power. This is power 2 times this power. So x squared plus y squared is less than 1, and 2 times x plus y is greater than 1. So power and plus and less than is overloaded. So this is actually a formula. So this says use Z3 to find solutions for x and y that solves for this formula. And then you can ask Z3 whether there's a solution. And if I already did it, then there's the answer here. So 1/8 and 7/8 is a solution here. Quick code. This is actually, I have a slide that shows a nicer use of quick code, and I will not give away what's the nice embedding of it yet. But let's. So this is a rough demo. Take it as that. So on the left-hand side, you have a column of dates. And on the right-hand side, you have one formatting of these dates. So there's one example of what output we want. So for each of these remaining rows, we want a particular output value to conform to this format. So suppose you are in Europe and in the US, then you write months and days in reverse, right? So in the US, they write the month before the day before the year. Or you can translate the 9th month to September. Quick code knows that something about dates because it's very common in spreadsheets. So it extrapolates that the left-hand column is going to talk about dates, and it extrapolates also what the meaning of the different entries are. So if you write dot or slash, so it's a smart auto-completion, by example. Okay. Daphne is a verification tool in a more traditional sense. So if you have so it's about program verification and verifying correctness and termination of programs. And in this case, the claim is that Fibonacci function terminates. And do you agree, disagree? Yes, it terminates? Okay, now we need the votes. So math, program correctness should be democratic, so we should have a vote. So one vote that it terminates. More votes? Okay, you're like laughing big face. What? Or you agree that it terminates? Okay, 2 votes that it terminates. And what? Depends. Okay. What does it depend on? Oh, if it stack overflows, then it always terminates. So it's going to stack overflow at some point, and therefore it really depends on how your compiler uses stack or heap, or other smarts. I mean, your compiler could actually be smart and actually detect that this does not terminate for n equals 2. So the usual Fibonacci function does terminate, but this has a typo. So it's, instead of subtracting 2 and 1, it adds 2 and 1. Right. So this is a plus sign, and it should have been minus to get the Fibonacci function, right? So anyway, at a high level you have a claim of termination, and then and the claim is that it terminates because every call decreases n, and then the tool gives some cryptic output that this is false. But the more fun thing is that it gives some squigglies in your code. So the point of this verification tool is that you do the semantic checking of the code while you code, so it gives you immediate feedback in an editor. And in this case, there's an editor in JavaScript that runs in the browser that gives you some amount of code annotation. Okay, so this is the website. So if you're tremendously bored during the talk, go ahead and play. I think we should start the...
Yes, I think that people a little bit puzzled that you start without introduction, but can I make it in Russian?
Yes, yes.
К сожалению, дело в том, что нам пришлось немножко задержаться, мы решали проблемы с видеотрансляцией, и за это время Николай успел, по-моему, представить все продукты Microsoft Research, но не представил сам себя. И я хочу исправить это. Николай Бьорнер — это ведущий исследователь Microsoft Research. Вчера он выступал на Яке, на секции интернет-математики, и там был действительно аншлаг. То есть люди пытались попасть в зал, несколько докладов подряд, у них это не получалось. И мы решили, что будет здорово, если мы также после Яка устроим вот небольшой такой семинар, причем хотелось бы сделать его именно в дружественной атмосфере. Вот почему появились эти пуфики, они как барьер между вами и спикером. Поэтому пользуйтесь той возможностью, что Николай Бьорнер сегодня здесь. Вы можете задать ему вопросы. Сегодня это намного реальнее, чем это было вчера в течение Яка. Вот. Ну и, собственно, let me give the floor to Nikolaj Bjorner.
Okay, thanks. Oh, okay. But I might stand here as well, but then I won't. Hopefully, I won't obscure the projector. Okay. So I gave a talk yesterday, somewhat high level, and the content of this talk is an expansion of what I talked about yesterday. It's designed to since the time of the talk is longer, it adds some room with extra material. It also has some additional breadth, but let's see. So to read off the slide, first I'll give some context of who I am and what I do and why not, of Microsoft Research in particular, and then continue the style of propaganda I just gave with the online demos. And followed by the meat of the talk, divided into two parts. What are the applications of theorem proving, and then the technology behind it. Now, the people come with different backgrounds and will be interested in different things. I hope that there will be a couple of takeaways depending on what you're interested in, and so for the context, one takeaway is the awareness of Microsoft Research. The propaganda is cool tools from research, in particular the software engineering related tools. Then in the applications category, the slogan here is that logic is the calculus of computation. And so what the applications highlight is the use of logic as the semantic basis of tools that do program analysis. Okay, so if you don't remember anything else, logic is the calculus of computation. If you went to university and learned analysis calculus, that is calculus for engineering. But now Z3 is a tool for logic, so it's a theorem prover. We call it a Satisfiability Modulo Theories solver, or SMT for short. The material I have on it is fairly technical, And so it will be at the end of the talk, and you can, if it doesn't work for you, then you can sleep or leave. But there's one. But if it okay. But there's one thing I wanted to point out in this connection, that so a theorem prover is a search engine, right? So we're in a search engine company. So it's a constraint search engine, and there are some beautiful dichotomies that the modern search engines are built upon. So beautiful principles of how efficient search procedures are built. And this was discovered around 10, 15 years ago, and has been refined. Now there's lots of details in modern efficient solvers that I will not go through. I will just try to give you a picture, high-level picture, I call it the mile-high picture, of what principles that modern search engines use. And this goes again and again in the special algorithms that we integrate in the theorem prover. Now, I rather address questions during the talk and delve into some details and skip a lot of slides, because I have about 3 times too many slides. Okay? So, can I get some idea what are you, let's see, what do you, of these items, which takeaways are you most interested in? So who's most interested in the propaganda and context? Who's most interested in applications? 1/2, okay. Who's most interested in technology? Wow. So it's a split. So nobody cares about the propaganda, but that's going to be quick. So here's the the team efficient S&T solver. It's developed by Leonardo Dumira, me, and Christoph Wintersteiger. There's an online video with a very simple example. The picture is taken from there. We're part of the research and software engineering group. And the mission statement is to improve software productivity. That group is part of the Microsoft Research Organization that does research in many areas of computer science. This picture is taken from the annual Tech Fest, which is like a bazaar, or well, it's a tech fest. Okay, so there are booths, and in each booth there's 2 or 3 researchers demoing their latest project, and projects are built like houses. You build them up and you tear them down, and there's a new project. So it's very dynamic in nature. So research does not ship products per se. We work with product groups that ship products, but one of the bigger stories from research was development of Kinect. So there was a paper on the technology behind Kinect that was submitted to a conference several years ago, and the reviews came back that the review said, this is totally impossible. Nobody can do this. You're smoking pot or anything, something like that. And they didn't get to publish their paper, but they shipped a product on it. Okay. So Microsoft Research Labs is worldwide, but it's still 1% of the company. Continuing with the propaganda, the core expertise of our group is around empirical software engineering, program analysis, programming languages, and foundations. And so I'm in the foundations. I'm mainly in the foundations camp, although I dabble a little bit around. So you will hear mostly about foundations. There's some nice tools, Specs for Fun, I showed you. You can also download it with Visual Studio. This is the Touch Develop on the phone. And this one is the auto-completion I showed you before. So this is going to ship with Excel, the next version of Office. So if you go into Excel, there's a new feature called Flash Fill. And so here I gave an example with a few examples. And suppose that you write John D with a period. I actually changed it slightly after I made the screenshot. Then you get, and hit Flash Fill, then you get an auto-completion, just like the dates. So instead of writing a script for manipulating tables, there's this automatic inference of your intent. Then empirical software engineering does code analytics. So based on check-in logs from project, it analyzes features of the code and the behavior of the how often people change the programs and so on. And it can be used for giving answers to what should I be testing, and this and there's a feature, derived feature of this in the Visual Studio 2012 Team Foundation server. So there was a talk yesterday by an engineer at Google envisioning this. So this is happening in Visual Studio. Okay. Here's the propaganda slide and Z3. And for those from academia, we have a internship program for academic interns, and we have several Russian interns. So we have a special Russian internship program. So I believe this is Alexander from and let's see, let's see, Sergey Puparev from Yekaterinburg works on AGL. The older gentlemen on the left and right are researchers; they're not interns. Okay, so now comes what half of the audience was interested in. The applications. So I'll start with one of the main applications of theorem proving. So let's see. I should stop speaking when? Yeah. Well. Okay. Yeah. That's essentially what I guess. But it's much better if there's spontaneous questions and remarks, because I can talk independently of the slides as well, and give you answers to things that you are actually interested in hearing. Yes. Yes, absolutely. And so there's a dedicated fuzz lab that runs on Windows and Office applications. And so there are a handful of people full-time working on, so there's one full-time research developer, and then there's a researcher who's Patrice Godefroy, who's essentially, his research is around Sage. And then there's a group in Windows, Windows security that owns the fuzzing component. PIX is something that you can use with Visual Studio. It doesn't ship with Visual Studio, but you can download it and add it. There's a component of PIX called moles. It's a mocking framework. So when you unit test code, you would also like to isolate certain components that hit disk or network, and that ships with that's going to ship with the newest version of Visual Studio. All right. So the point of these tools is that they perform code exploration based on constraint solving, and you can use this for smart white box fuzzing. To put some anecdote around it, I saw this bug report a few months ago, and so this is from a developer who does not know what the tool does underneath, but this is an example of a bug that was exposed by Sage, and so what it's able to do is to carefully, just like the example I showed you, find the magical values that cause a sequence of events to happen. And so it's able to do this code exploration that people will have a hard time doing. So the question was, is Sage used in production? So here's the slide that, the bragging slide. about Sage. It's run for hundreds of CPU years for hundreds of apps. So you can deduce that each app we spend easily a CPU year just analyzing each application using this tool. But that's useful because if you have a billion people depending on tools and there's a security vulnerability, one CPU year is nothing. There was recently a security vulnerability in Java that was found. Okay, so it's also the largest use of a constraint solver. Yes, good. Files. Sage is a file fuzzing tool. No, network fuzzing is a tough nut. Yeah. So Sage is very simple. You have an executable that takes a file as input, and so the input to Sage is one executable and a seed file, or maybe no seed file, but at least the assumption is that the executable takes as input a file. And there's many network-facing interfaces that are of that nature, and they are especially embedded in browsers. Network fuzzers, the big problem with network fuzzers is, of course, the how to isolate them. In principle, you can do network fuzzing, but in reality, how to clearly isolate what is an input and what is a sequence of event. Okay, test case generation. So what's the principle behind it? And this is by an example of a greatest common divisor program. So this computes the greatest common divisor of x and y. And suppose we want to execute the loop twice. Then let's unwind a trace where the loop is executed twice. So the first time we test for m equals 0, it should be false. The second time it should be true. And now we added timestamps to the variables. So every time we assign to a variable, we increment the timestamp, or we initialize the timestamp. So that allows us to rewrite assignments to equalities. So now you have a logical formula instead of a sequence of instructions. And so if this logical formula has a solution, then the solution where x0 and y0, so the values of x0 and y0 in the solution will be an input that forces the trace, the execution to exercise the trace twice. Okay, so here's an example solution that does it. And this is where the solver is used. It takes as input the logical formula and then finds these values of x and y, so x0 and y0. Questions, comments? Yes? No? No, not necessarily. So it's so what exactly? Which solution? So the input to the constraint solver is a formula, and it totally depends on how search is organized, what solutions it finds, and sometimes we give back that gives back a large number as a solution, and there are cases where that's very undesirable. And two cases are when the solutions are printed to users. A common complaint about PEX was that, oh, you give an attack string on your file path attack string, but you have these very funny characters. So if you can find Roman characters or normal characters from your usual alphabet, or the Cyrillic or Roman, it will be more readable. Another example is when an input is used to allocate memory, then it might be legal to allocate 4 gigabytes of memory, even though it's legal to also allocate 10 bytes of memory. And so if you run the test case with the allocation of 4 gigabytes of memory, the execution according to that run will bog down the computer and so cause a memory, an out of memory error instead of really exercising the trace. Maybe you also want to exercise out of memory errors, but you also want to exercise traces where you don't have the out of memory conditions. So what PEX has is an optimization phase. So we give back a solution, and then you can try to look for a smaller solution, a numerically smaller solution. Very good question, thanks. More? This is the main loop of the test case generation tools. They start with an initial input and then run it and extract the sequence of instructions that were executed during a run. And they record the executed sequence of instructions in the database of known paths. And then take one path and see if you can flip a branch condition. So negate one of the branches on the path. So that could, so if you have an input that satisfies the new path, then you can, you have a new execution coverage. So that's a constraint system, it gets solved, and so it goes around. So that's test case generation. Here's an example of use of bit-precise reasoning in program analysis. So internally we have, so Microsoft bought a company called, I think it was Intrinsa, about 10-15 years ago, and it developed a tool called Prefix, which does static code analysis, and it contained, according to the slogan that logic is the calculus of computer science, also Prefix has a dedicated constraint solver. So at some point we worked with the developer of Prefix at Microsoft to integrate Z3, and his constraint solver is efficient but very partial. And so by integrating Z3 we were able to do bit-precise reasoning, and we found a number of bugs in code that depend on the semantics, integer semantics of machine arithmetic. So here are two examples. So one is the binary search algorithm, and that was a bug that was in Java. It's a well-known bug in Java. And the bug with the binary search, and sorry, the PowerPoint version of these slides is animated, but what you have here is a program that takes an array R and a low and high as input, and then it finds, the assumption is that the array is sorted, and you want to find a value that matches also an input key. So the key is also an input to this function. So it does a bisection search, and the problem with this statement is that if low and high are more than half the maximal integer, then if you add these together, you get an integer overflow, and so you don't get the middle point between high and low. So there are easy fixes to this bug by subtracting high and then adding it again or something like this. But the point is that these kinds of bugs appear because when we normally program, we think in terms of standard integer semantics, not in terms of the integers that run the semantics in Java or in C, C++. And this one is taken from Koenigen and Rich's book, well-known book on C programming. So it's a classical. In the first edition, they gave an example of a program that converts an integer to an ASCII string. And it starts out, if the integer is less than 0, then append a minus sign to the string, output string. and then negates the integer. Right? So now if the integer is int min, which is 2 to the, which is the bit string of all zeros, so it's minus 2 to the 31, then if you negate minus 2 to the 31, you expect to get plus 2 to the 31, right? But there are only 32 bits, and we also have to take care of a 0, so there's actually only 2 to the 31 minus 1 positive numbers, and so there's one more negative number than positive. So in the second edition of this book, it was left as an exercise to fix it. So I used to work in a startup, and we always asked this as an interview question of how write the program to convert integer to ASCII. So it's I guess it's also an interview question more than in several other places. But Königin and Ritchie overlooked it as well. So what's behind analyzing such programs? It's bit precise analysis. So there's a theory, there's a way of formalizing what are integers on a machine, and the theory that's relevant for integer is called bit vector logic. So in bit vector logic, you can add vectors of bits, and you get modular arithmetic. So here we have two numbers that have 6 bits each, and then when we add them, we get this result, which has, and since there's an overflow, the upper bits are all 0, but so it's let's see, it's 1, 2, 4. So the result is 4 modulo 2 to the 6. You can also do bitwise conjunction and take the conjunction of each bit, concatenate bit and extract bits. So what lies behind that is the solvers work in terms of these kinds of objects and operations, and figures out whether formulas over these are satisfiable. Questions? Yes? Application? Multiplication, yeah, right. So that's like, that will be in the modular arithmetic. So you can also multiply bit vectors. And that's actually quite expensive to reason about. So you throw bit vector multiplication at solvers, and they sort of chuckle along or die. So this is one of the challenges, so we're not aware of any efficient reasoner for bit vector multiplication. Now there's a famous Russian mathematician, Yuri Matyasevich, who showed that solving feasibility of Diophantine equations, so equations with multiplication and addition over integers, is undecidable. But for bit vectors, it is decidable. It's all finite domains. So the bit vectors are fixed width, so there's only a finite number of combinations. So you can have Diophantine equations over bit vectors and solve them, assuming that you can take care of the combinatorial explosions. So here's another application. I think I'm quickly running out of time. So this is program verification. It was a big project we had some years ago of verifying a large hypervisor core. This is, I'll go a little bit quickly over this. So you map a program into an intermediate format that maps into formulas, and that gets checked by the prover. And lots of details on the slide. I'll just go over the one war story from this project. So they ran regressions every night on all the modules they had been verifying, and took the timing of what. So each color is one of the modules, and then the vertical axis is the time it took to verify one of the modules. So, so in some cases, the verification time got slower, and when we changed the intermediary verification format, the encoding of verification condition got slower, and then when we improved the theorem prover, it got maybe 100 times faster in some cases. What it really illustrates is that much of what we do in theorem proving and stat solvers, they're driven by benchmarking and applications. So we look at the challenge, the formulas we get from the applications, and then develop and find structure in these, and that gives rise to more efficient search algorithms. What are you willing to? Are you willing to wait for your theorem prover to finish? Apparently, you're willing to wait up to 5 minutes until you lose focus, and after 1 hour, you totally lose interest in theorem proving. So theorem prover better give feedback quickly in these interactive scenarios. But nevertheless, you actually get some happy users. So this was an email that our German colleagues sent to each other and was forwarded to me. And I don't expect, so Microsoft is a multinational company, so these are, they write in German, and then we can use a translation service to translate from German to Russian. So I downloaded a new browser and tried the translation service today. So if you can see that I'm using the politically correct browser. I normally use Bing Translate on the slide. All right, so we also have a research operating system called Verve that was fully verified for memory safety, or at least this version of the operating system was. And the clever part of Verve is to use typed programming languages and assembly code to take care of most of the code of the verification problem. And then there's a nucleus that's written in assembly language that is verified the classical Floyd Hoare style with Boogie and Z3. So Boogie is a verification condition generator. It takes as inputted program and generates a formula such that if the formula is true, then the program is correct with respect to whatever you said about the program. Okay, so then there's an application string analysis that I will not go through. And now we have SMT. What is SMT now? So I talked about applications, so now the other. So those who are not interested in SMT can leave now, and we can. What is SMT? By two examples. Suppose you have this formula x squared plus y squared is greater than 1, and x times y is greater than 0.1. Is it feasible? Yes, it's feasible. So this was an example value that satisfied the formula. And here's another formula that if we constrain x times y to be greater than 1, is that still feasible? Well, we know that from geometry because this is the unit circle. So is there anything in the unit circle and then when we multiply them by each other, so if we multiply two numbers that are less than 1, will the result be greater than 1? So yes, it's unsatisfiable. So this is what an SMT solver can be used to answer. So we can answer such questions whether formulas are satisfiable or unsatisfiable. Okay, so is this clear? Is it mystery or is it too clear? In the middle. Okay, so so the main points to take away is that on the left-hand side you have a logical formula. You have constraints. You have statements that say something about unknowns, x and y. And the question is, are there values for these unknowns that solve these constraints. There are solutions. And the whole point of the theorem prover is to tell you whether there are solutions or not. And it can also tell you which solutions there are. Okay, so Sage uses the solutions to give program paths. Here's another more involved example that illustrates the use of finding solutions for formulas that have a mixture of different components. So this uses addition, and it uses select and store, which are so-called McCarthy applicative maps, or McCarthy array theory, and a function symbol f. So it uses arithmetic here. It uses the array theory, and the array theory gives meaning to select and store. So the store term takes an array, an index, and a value, and if you select back the index, you just update it, you get back the value. If you index on something that's different from what you just updated, then you get back the original, something that was in the original content. So if you have a program that updates an array, you can treat it as taking the original version of the array and updating it with respect to those values. So you can translate programs that operate on arrays into this kind of formulas. Now this formula is true because y minus 2 is going to be equal to x. So we're going to select an x here, and we'll get back 3. And now f of 3 is equal to f of y minus x plus 1, but y minus x plus 1 is 3 because of this assumption. Right? So if you take y minus x, you get 2, and if you add 1, then you have 2 plus 1 is 3. So f of 3 equals f of 3. So an S&T solver can be used to solve for this. And right, so it doesn't matter what interpretation f has. Here's an example of job shop scheduling. The task. Okay, so you have tasks and machine. You want to match them to each other. You give constraints. Can you run? Each job should run on one machine at most. Each resource. You can't run 2 jobs at the same time on a machine. So these are resource constraints. You can express this in logic by associating a start time with a task and a duration. And a point here is that the formulation of the resource constraint is a disjunction, so it's a non-convex feasibility problem. And so here's an example. Sorry, it's very quick over. And I see, strange. Let's see if it comes, no, well, this didn't save the right way, but anyway. So if we take a selection of these constraints, we get a set of inequalities. If you have only 2 variables per inequality, you get essentially a graph path problem. And so if you look for a negative cycle in this graph, then the constraints are infeasible. So this subset of constraints are infeasible, and you can use efficient, dedicated algorithms for doing the graph search. So 2 classical graph network algorithms are the Floyd-Warshall and the Ford-Fulkerson algorithms for graph feasibility. Okay, so there are several tools using Z3. Many of them are research tools, and so they have funny logos. Poirot is the one with the bowler hat, and Daphne is the one with the slightly undressed woman. But it's a program verification tool. Okay, so here we have Sage is used heavily, and it ships with the static driver verifier since some years, and we started using it in Azure. In the community of S&T solvers, we also have competitions to evaluate different solvers. It has progressed the state of the art quite a bit. So sometimes we participate in the competitions and do very well there. Okay, the research is on algorithms, data structures, heuristics, and decidable fragments. And with logic, you can express logic can be very expressive. Is a very expressive language. So you can write short logical formulas that have a lot of information content, or more. To say it in a different way, there are classes of formalisms that don't have whose witness generation is increasingly hard. So propositional satisfiability is known as the NP hard class, but there are other classes. First order logic is semi-decidable, then there's quantified Boolean formulas that are piece-based complete. So the decision complexities for the various classes of formulas that are handled by the theorem prover grow quite significantly. But then we have specialized procedures for each of these classes. And then the highlight here is that since we're not interested in solving random formulas, we solve formulas that come from applications, and these often have structure that can be exploited. So this is very much name of the game in the SMT area. These are three concepts, little engines of proof. The research around it is on decision procedures, combining decision procedures and dealing with quantified formulas. So here's a set of references to that. There's also an introductory background reading on SMT. So if you, the previous slide was for the expert. This slide hopefully is for is more digestible. It's appeared in the communication of ACN last year. So there's an introductory article to what is SMT. So that will give more background on this. Okay, so here's the second last takeaway of the talk, which is from the mile high perspective. But okay, let's see how much we'll go through of this. So I said that Z3 is a search engine, right? It searches for witnesses of satisfiability of logical formulas, and it uses it exploits a dichotomy of searching for counterexamples and proofs, and it does that at the same time. So it searches for either there's a witness that the formula is satisfiable, or there is a certificate that there's no feasible assignment, that there's no satisfiable assignment for the formula. And this is a common theme in most modern SAT and SMT solving algorithms. So in between, when you can't extend your current model to a full model, there's a conflict resolution step, and that allows the proof procedure to do back jumping, to search back, to backtrack into a state where it can, where it has a chance of finding a model. On the other hand, if you have some partial proof, you can use that to prune the search for models. So this is actually the modern SAT solver in one slide, and the only thing you should understand from this is that there is you can give one slide description of what modern SAT solvers do in a nutshell, and but nevertheless, even experts can, it can take years for experts to really grasp what's going on. So I recently had ice cream in Trento with two leading SAT experts, Matt Soos and Nikolaj Sørensen. So Matt was making this comment. I was looking at your code for a year and I couldn't understand what it was doing in this back jumping loop. And the point is that there's this, it maintains a certain invariant that you derive a conflict clause. So hopefully, if you're interested in looking at SAT solvers, you can look at the source code, but take a look at this slide to say what the main invariants that the code does. So going back to the mile-high perspective is that there's that there are two components that are important when you write efficient solvers, is to get ways to efficiently backtrack from failed model search attempts, and then have efficient indexing to extend models. So a lot of the algorithmics and data structures that goes into searches is around doing these indices and algorithms for both the backtracking and the propagation. All right, so we have two research directions. One is solving horn clauses. So I think I'm going a little bit over, so I'll flash these two slides, but you've been silent for a little bit too long time. So, okay, so these two slides on research takeaways. So this is the second to last slide. This last slide has conclusions. I don't want to hold you too long, so please ask questions, and I can go back to slides, or you can leave, or yeah. Yes. Good. Yeah. So the I2A and binary search examples were, identifying overflow bugs that caused wrong program behavior. So you have in a program you have the possibility for an integer overflow, and then correct programs may have these integer overflows, but they will also check for them. They will have code that checks or prevents them. So if they have code that prevents integer overflow, well, there's no feasible path that will get to it. If they have code that checks for the overflow, then the overflow is also benign. So in a static analysis tools, you essentially enumerate symbolic paths for the program, and then you add checks for every time you have an integer operation, multiplication or addition. You can check whether it overflows. If it overflows, but it has a test for the overflow, then it's a benign one. If it doesn't have a test for the overflow, then there's a feasible path that goes through and then accesses some memory based on the dirty value. So this is something that the constraint solver can tell you. And so this is what we did with prefix. And similarly with PEX, which is a totally different tool. So prefix is a static tool. Now PEX is a dynamic tool. It does these executions of programs. It will also be able to generate overflow values. And so for the binary search example, it will find values for the low and high inputs where the mid value is negative, and that will be out of bounds of the array. So it was basically look for a test input that violates the bounds condition, because there's an implicit branch in the program. So that's another way. Yeah, you can give it to PEX. Yeah, give it to PEX. For the binary search, nothing. It takes 0 seconds. It's a small. So with prefix, we ran it over the Windows 7 source code. Actually, not all of it, but we ran it over, I think, half or. Windows has many enlistments, and so we ran it over the main branches, and that took a few days to run on one machine. So yeah, depends on your setup and how much. But this was for millions of lines of code, not for binary search. Yes. Verve, yes. Verve is very... So hypervisor was done a few years ago. The verification project on hypervisor is over. What was verified was 60 or 70% of the code correctness of the shipping hypervisor code. The Verve research project is ongoing, and there's some garbage collection and other things that are added. Yes. So there's an Australian project that has been on verified operating system where they used Isabelle with using a quite different methodology. I think it's called maybe not, but yeah, LLPC or sorry, but that uses a quite different methodology. It wrote the operating system in a functional language and then did refinements from that. Oh yeah, but Verve is a one-man. So Verve is a small research project. Singularity was a bigger joint effort, and Singularity was only released several years after they started working on it. So Chris does release Verve. So in the Singularity distribution, there's Verve code. This is a question for Chris Habwitzel. I believe yes. I think he's working on. Actually, that's an interesting question. I have. There was an announcement yesterday about touchscript.org. Oh, okay. So that's a typed extension to JavaScript. No. Okay. TypeScript, not touch. Okay, sorry, I was doing touch develop too much. Okay. Yeah, new exciting announcements about touch develop are also soon. So keep your excitement. This is not it. Sorry. Is it TypeScript? Oh, this is a different browser. Okay. TypeScript. Why do you have a Google browser as default here at Yandex? I use Bing. Yeah. Oh, here we go. This seems like some blog. Maybe if you are lucky, he has a link to it. So this is typescriptlang.org. Okay, that's the link to the tutorial. So that's has been in development for some time now and was just announced yesterday. So that's a type. You have type. You have a typed classes and other attributes for. Okay, so here is an example. So you can give now you can give types to your JavaScript. So it's an extension to the language. So there's so there's some emphasis on supporting tools for JavaScript, since it's incredibly important for web programming, and Windows 8 has strong support for JavaScript. And the APIs for writing applications for Windows 8 are also, there's a common nucleus that allows you to write JavaScript and C++ and managed code as well. So the tools for C++ are also stronger in the next version of Visual Studio. Oh yeah, so VCC, the verifying C compiler, is for C, the C programming language, and that's a really tough. The VCC compiler does thread safety, and so it's really the annotations you get for that they're not for kids. And if you have a type-safe language, you have certain advantages. Now, the research that we do in our group spans, the VCC compiler came out some years ago from us, but then there are other researchers who do these kinds of type-safe extensions or languages that compile into JavaScript. So there's a lot of research. Research-wise, JavaScript is a hot topic. Product-wise, I know that from Visual Studio emphasizing more on supporting C++ and C. Yeah, but no, I don't see it like this. So I'm not involved in these things. But here's how I see it. And the world is there are many programmers use many different environments and languages to write their programs. And JavaScript is getting a de facto language of writing apps on the web. So it's in our interest to support that well, and in a .NET is really cool, and you can write efficient code, but you will target a fraction of developers with it. So you will support some fraction of developers, but you won't support the whole range. Okay, this goes. Okay, I think we're getting out of my level of expertise, but we can try to take it offline. Thanks. Yes. So PEX is based on the Common Language Runtime, which has consists of a bytecode. So there are bytecode instructions that are emitted as part of compiling C# code into the common IL language. So that's corresponds to Java bytecode. Yes. Okay. And then there's there are runner infrastructures for intercepting bytecode instructions. And so PEX has hooks into these into the jitter essentially and the runtime to extract the stream of instructions that are executed. So it takes this stream of instructions and compiles them into formulas. So assignment instruction becomes equality and so on. Yeah? And Sage is different technology. It uses a virtual machine layer called TrueScan Nirvana, IDNA, which is, I don't think it's an internal tool, but it's basically something like an LL. You can think of it as an LLVM that sits and can record also your instructions that are executed. Yes? Yeah. So we basically prioritize the exploration of paths according to block coverage. So if you execute a loop many times, we're deprioritizing repeated executions. So it basically means that these tools that find bugs based on symbolic execution will defer exploring long loops. So it may not be able to catch those. Now, if you have a loop that executed many times, you can often compress the effect of an execution. So the formulas that we end up handling are not as big as the repeated execution. Right. So if you increment a number 1,000 times, the effect is x plus 100, not x plus 1 plus 1 plus. Okay, so I think we're well over. Oh, sorry. Yes. No. I think it's context dependent, and so the hardcore verification give a sophisticated correctness argument and proof of a program. Does not make economic sense for programs that you write and rewrite. It's just it doesn't make sense to me. And you can make tools automatic and fast and so on. It's still besides the point. But in the case of Sage, it's run as a service. So there's a room for running tools in a service environment when they're automatic. So I think that's a good model. Then there are models of using theorem-proving technology in various contexts. And I gave a slide of all these different tools, and some of them use the verification in quite, not for program verification, but for semantic analysis of configurations. And there are applications for that. PEX is some people like to use PEX and use it and rely on it, but it really depends on whether you also are disciplined to write unit tests and assertions. So if you don't have a process of writing unit tests in the first place, it doesn't. You're not even there to use a verification tool. Right. So Set3 has many bugs, and and we try to fix them as quickly as possible. And we're never going to verify Set3 as well. But we generate certificates, and there are so we generate proof objects, So the Isabelle theorem prover uses set3 as a tactic, and Isabelle is based on a trusted kernel, which is much smaller than set3 and is widely believed to be very correct, and so it reruns proofs. So it gets the certificates, the proofs from set3, and then reruns them as tactics. So in that sense, you can use a program that has bugs as an untrusted oracle in high fidelity contexts. And then there are other applications where it doesn't matter that set3 has bugs. If you want to generate test cases, it's not your it's not the same as releasing an embedded system that does cryptographic keys with high fidelity. Yes. You can if you check the certificate. If you ask set3 to generate a certificate and you check it, well, we give you a way to check it much faster than searching. No, you should not believe it, but you can check it. We give you a way to double check. We show our work, or we show the result of the work. No, PIX only gives you certificates of paths, which paths exist, not that there is no path. So there are other tools. I flashed over this horn clause research, which is something I do currently. And that's okay. I'm not going to show it, but that actually gives you certificates of both correctness and incorrectness. It's also a question of whether the algorithms are complete for this, or memory. I mean, there are small programs that we never return on. Because you can I had a slide on the complexity measures of formulas. So some problems are NP complete, and other some problem classes like propositional satisfiability is NP hard, and then. But when people express properties about programs, they might use logic with quantifiers and arithmetic, which is highly intractable. So there's not even a complete algorithm for deciding these formulas. Okay. You're talking about modularization? Are you asking whether there's a modular approach? Oh yeah. So Floyd-Hall logic is modular. Oh. Yes. Yeah. So standard. Yes. That's up to the applications of my theorem prover whether they do modular style. Yes, of course. Mm. Okay. Okay. Yes. 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 Okay. Okay. That's pretty much. So that's in the spirit of the fuzzing, and in the fuzzing world, you have the black box fuzzers that genetically modify a seed, and but don't really have the tools to look inside what happens as an effect of so most black box fuzzers just look at the seeds and start genetically modifying them over a Markov model. But the white box tools will also have a Markov model to modify seeds, but use this as a bootstrapping, as a stepping stone to find the right modifications that will. So maybe your genetic modification will not expose the bug path, but be close to it, and this is where the constraint solver can tell you. What? Okay. No, you don't. Sage leverages something like what you describe. It leverages seeds plus modifications, but it goes beyond that. So it leverages that there is a set of seed files that will execute, exploit different parts of the programs initially. But these seed files will never cover everything. And you can genetically modify each of them a lot without ever really falling outside your cone of influence. But Sage is able to find the magical needle in the haystack that gets you to the bug or to the security bugs. And let's see if I understand. So, what is the protection of? Yes. Overfloating. Right. So Z3 can run out of memory during its checking. One thing to note that if things are purely, if we have multipliers, then we use quadratic space to represent multipliers. And if you have many multipliers, we can consume a lot of space. But during search over ground formulas, so formulas without quantifiers, we actually don't need to add we don't need to grow space during search. We grow space during a pre-processing phase, and then search itself can manage how much memory it exploits. So that's a characteristics of how SAT solving technology works. It doesn't necessarily need to grow space during search. So that's the good news. The bad news is, of course, that sometimes you express things in more expressive logics where we don't have space-efficient algorithms that will consume asymptotically a lot of space. And then we overflow, run out of memory. Now in Z3 we tune it mostly to, in program verification, we tune it to give answers quickly, to give unknown quickly, as opposed to go on to tailspin search. And so we rather say unknown, we don't know, instead of just going. I'm so surprised, so many questions. Okay, no, Z3 is not open source. It's free for academic use. If you want to use it for non-academic purposes, you can buy it from. We have it